Okay, if instead of doing a repeated measures ANOVA, you want to assess change right within the general linear model, you really have two basic options. And this is if you have specifically 2 measurement occasions. If you have more than 2 measurement occasions, you have other options. Repeated measures ANOVA is fine for you to use in that situation. But if you only have 2 measurement occasions, like a pre-test and a post-test, you can do and assess those sorts of type of change right within your standard GLM or regression model. And you could do it in one of 2 ways. The first one is calculate the difference between pre-test and post-test. And the second one is predict the post-test from the pre-test. So the first one is the difference score, and the difference score means exactly that. It's calculating the difference between time 1 and time 2. Sometimes people will call this a simple difference score. Whoop. We'll call it a simple difference score or a change score or a gain score. Sometimes it's also called change in y, delta y. To create a change score, you use subtraction. You take where they are at time 2 and you subtract where they were at time 1. So change in y is an estimate of the amount of change that has occurred between your 2 time points. It's really nice because it has high face validity. It's intuitive what it means. I know if you knew 7 things at the beginning of the year and you know 9 things at the end of the year, you learn 2 things. It's most often used as an outcome. I don't know why I wrote predictor. But we want to predict how much change has occurred, so this is often used as the outcome variable. So when you want to use a difference score, it's when you're interested in measuring just how much change has happened. So oftentimes that is a question that we have. If you've done something, I want to know how much different you are now than you were before. How much did you change? If you want to estimate a difference score, you have 3 requirements. Both times that you measure the thing, you have to measure it in the same way, on the same numeric scale, and you want to minimize your measurement error. You want to have really good reliability if at all possible. That's just generally good practice, though. Now, the second way that you can do it is something called residualized change, and that just means take your post-test score, predict it from your pre-test score. With residualized change, do you remember residuals? Which one of these is the residual?
The E.
The E. Got it. So to get residualized change, we're going to regress the time 1 score onto the time 2 score. And so basically what we're doing is we are using this model to predict where we end up at time 2 based on where people were at time 1. So let's think for a second about what this means, essentially. If I have time 1 on the x-axis and I have time 2 on the y-axis, and each point is a person, you can see that people's scores at time 1 are related to where they were at time 2. I'm pointing at this like you guys at home can see it. Maybe I should point at it like, I don't know where you see me on the screen, so never mind. So these are residuals, distance from the line. Did I do a good job of predicting you or not, is basically what this means. So looking at this, what does it mean if I have a large residualized change score? What would that mean? It would mean, so that's, you're showing me that I didn't ask the question right. Let me ask it another way. If an individual person, which one of these people, these dots, has a big residualized change score, has a big score? this person. They're really far away from where I expect them to be. So if I have a residualized change score that's very big, it means I did a really bad job of predicting where they are. If it's really close to 0, it means I did a really good job of predicting where they'd be. And if it's negative, I could also do a not very good job of predicting where they are, just in the other direction. What about a difference score, a delta y, that's really big? What does that mean? Yes, people talking. 3.
Dr. Nolan, to clarify, so you're saying that you're using time 1 to make a prediction, and then you're using that prediction to compare to what you actually got in time 2. Is that correct? The errors? Okay.
Yes, exactly. With a very large delta y, it just means a lot of change happened. A very small delta y means not much change happened. So I brought that up to sort of say, to show you this little crosshatch here, that if you're using these two methods, they are talking about slightly different things. They answer slightly different questions. But you can use them in very similar ways, and I'll show you how. So I have an application that I've done where I have a pre-test and I have a post-test, and I have kids who have disabilities. They have an individualized education plan, and I have kids who don't have disabilities. And I'm looking at how much they change in their reading scores over time, from pre-test to post-test. This is a little bit about my sample. I have about 450 kids in this sample. About half had a recognized disability. They're all about 4 or 5 years old. So I have this, it's also called an ANCOVA because I have a covariate. So they call it ANCOVA. It's just a regression model. It's a GLM where I have time 1 that I'm using to predict time 2. So there's the equation of what it looks like. I have the y of time 2, and it's equal to my intercept plus b1 times time 1 plus b2 times my whether or not the kid has a disability, IEP status, and then plus error. I'm going to skip over this because you should never ever do two-step residualized gain. But I'll tell you what it is in case you ever see it. In two-step residualized gain, I fit one model, time 2, predicted from time 1. I save the residual for everyone. And then I fit this new model where the residual is my outcome. And then I'm going to see whose residual is bigger, kids with an IEP or kids without. You should never ever do that.
Why should we never ever do this?
You should never do it because general practice within statistical land is to do everything in one step if you can. Because every time that you do multiple things to your data, you're adding potential error. Also, I just think it's confusing. But maybe I'll just show you the rest of the results of this and then you can decide. Maybe you'll see them. I don't know. Here's that simple difference score I showed you before. The y is time 2 minus time 1. And then this rest of this regression equation is the same. Oh God, we're not doing that. I thought I took that out. Okay, so here is just my distributions generally. Here are the typically developing peers. And here are the kids who have an IEP. You can see that there's a difference between these two groups. This is them at pre-test. This is them at post-test. You can see that there's sort of differences between them. So here what I've done is I have given you a histogram of the simple change. So like right here are kids who have negative gain. So these are kids that lost ground over time. Then we have kids who made a little bit of gain, and then we have kids who made a lot of gain over time. The next thing I did here was look at the correlation between time 1 and time 2. This is the equivalent of that other plot that I made for you earlier, but this is with actual data now. So here you see some kids have a really small residual, they're very close to that line, and some kids have a very large residual, they're far away from the line. And what I've done is color code them by whether the kid has an IEP or does not have an IEP. Just so you can visualize what this looks like. So here's what I've got here for the results. So remember what my equations looked like. I had, for the one-step residualized gain, that was time 2 is predicted by time 1, and IEP status. When I do that, I have my intercept here is 29.92, so that's saying for kids who have a 0 in the fall and who do not have an IEP, our expected score in the spring is about 30 points on this assessment. For every additional point on fall score that I go up, controlling for IEP status, every additional point I go up is 0.75 points in the fall, in the spring. And I conclude that there is a significant difference between kids with and without an IEP. Kids with an IEP are gaining less during the year. And my R squared is 64%. Here's that two-step residualized gain method that I went on and on about, where you've done one model and then you extract the errors and then you're going to predict another model. The outcome in this case is error, is your residual. My intercept here is 2.4. So this is why I say this one's difficult to use, because let's try to interpret that. Kids without an IEP have an average residual of 2.4. It's just not a very clear argument. Look at my R squared, it's only 4%. But I, again, am going to conclude that there is a difference between kids and without an IEP, that kids without an IEP are gaining less during the year. And now the last one I'm going to show you is that simple difference score, where I have a change as the outcome. So in this case, the change is what my outcome is. I just said that. So again, I don't have fall score in the model because my model is just change equals IEP status. So here, my intercept is 11.6, and I'm interpreting that as kids without an IEP are gaining about 11 points. And the difference between kids with and without an IEP is about 1.8 points in how much they gain. And that's not significantly different from 0. And look at my R squared, 0.6%. IEP is not explaining very much about how much differently these kids gained. So I get completely different answers depending on which one of these I looked at, which method I used. And two things you need to know about this. The first is that we are well aware that this exists. This happens when you have differences at pretest. If there are a difference between your two groups at pretest already, this will almost always happen. These two methods will give you slightly different results. It's so well known that it has its own name. It's called Lord's paradox, which is just fun to think about. But I like using this example because it demonstrates that these two methods, essentially, these three methods really, they're asking all slightly different questions. So you're going to get slightly different answers every time you look at it because the question is somewhat different. Here we're asking, did they gain differently? And here we're asking, do they end up differently, controlling for where they start? Is that just me saying, look at the R-squareds? Here I've just sort of re-highlighted for you the differences between these equations, my one-step residualized gain, to sort of show you what this equation looks like if you pull and plug the numbers in. I did that for all three of these, my two-step residualized gain and my simple difference score. Controlling for where we start, that's the residualized gain. Yes, that's correct. Whoops. Oh no. So I want to show you one more thing, which is there's one more way you can handle these, which is including the time 1 score as a potential covariate. So even though I have time 2 minus time 1 as my outcome, I can still control for time 1 within this model as well. And if you do that, what I want to show you is that this is the output from that model where I've controlled for time 1. My R squared now is considerably bigger. It's 13%. Before it was 0.6%. I don't know if you remember that. So this is time 1 I've controlled for. It's statistically significant. Now I see that I do have a significant effect of IEP status. They're ending up in a different place than they started. And you get exactly the same results as you do for the residualized gain model. Time 1 times your pretest times B1, and then your other predictor is IEP status. So anyway, when we control for time 1, the coefficient associating IEP with your outcome is identical as it would be if you are just using your standard residualized gain model. But you still end up with more variance explained in the second model in the first model than you do with the second. And so that's why I like the residualized gain model, because you end up with such better, with more variance explained. Come back, I want to go up. I'm going to go back to this one here so you can compare the three. In this case, 64% of the variance is explained in your outcome. So if you remember the things that we looked at before in terms of the equations that we use to calculate our B weights and our beta weights, those become more powerful the more precise we are. So the less error is in our model, the more precise our B weights are. And so if you have only 2 time points, this is a really nice method that you can use to examine how much change is happening, staying within the GLM or within the regression-based models. So when you see papers that have been published that have 2 time points, oftentimes this happens with an intervention sort of study. You'll have a pretest and a post-test and some sort of intervention in the middle. And this is usually the method that I will see used in those situations. This one-step residualized gain. Okay, ask a simple question, Adriana, and get a very complicated answer of 27 slides worth. But that's what I wanted to tell you about with the residualized gain.